Okay, so greetings again, everybody. This week, which is the week of April 6th through the 10th, we're going to cover two major topics in 155. And those two topics are searching and sorting. Okay? Searching and sorting. So the first one we're going to look at today is searching. Now, searching and sorting are sort of related to each other. Generally, we consider that the input to a searching algorithm is a list of data or a set of data, and we want to know if a particular value is present in that data or not. Sorting is similar in some ways, but in that you get a list of data again, and then you take that data and you reorganize it into a sorted version, a sorted permutation of the data. Okay, these are two basic fundamental algorithmic processes that computers have to do all the time. They're so basic that it's a good place. It's a traditional place to start talking about algorithmic complexity, which is something we're going to broach today. And they're also easy to understand, but they are deep. And they can be complicated, especially sorting. And so there are going to be some concepts here for you to wrestle with and incorporate into your knowledge banks. Okay. So today we're going to look at, like I said, searching. And there's two types of searching algorithms that we are going to be looking at. I'm going to open up a blank screen here. So today we're looking at searching algorithms. Okay. The first type is linear search, and the second type is going to be something called binary search. And we're going to kind of look at both of those. We're going to compare and contrast what each of them looks like. Okay. So in order to facilitate this, what I've done is I've gone over here and created. Well, I didn't create it. I found a web page that allows us to emulate using a deck of cards. Now, there's nothing special about cards. Any set of data will do, but cards are a good visual indicator of what I'm talking about. I usually use playing cards actually in class when I'm introducing the idea of searching and sorting and looking at the various algorithms and comparing the various algorithms. But of course we're not in a physical space together, so a virtual deck of cards will have to do. Pay no attention to the queen over here. I've eliminated her. She's a face card. This is a stack of randomly shuffled cards. Your standard 52 card deck. All right, and prior to our starting here, I created this stack of cards. Okay, here let's add a few more. Let's get rid of the face cards because they complicate things. But we'll treat that as a 1. Here's a 10. Okay, get rid of the face card. Here's a 7. Okay, so there's a stack of cards here. Now someone handed you this stack of cards. Okay, and you don't know what's in there. And someone said to you, hey, and we're going to ignore, to make this easier, we're going to ignore the suits of these cards. In other words, we don't care if they're diamonds, hearts, clubs, or spades. All we're looking at is the number. If someone said to you, hey, in this stack of cards, is there a certain value present in that set of values, in that stack of cards? How would you find that out? Well, all you know about this stack of cards is that it contains a series of values. Okay? You can only see the top one. All right? And that's true of any computer system that is making use of a set of values. You can only analyze the top value. You can only see one value at a time. If you don't know anything else about this, if you can't say, all I know is that there's a set of values and it's in some order, okay? It's not sorted. It might be, but we can't assume that. I can tell you for sure it's not in this case. but we can't assume with our set of values that they're in order. So is there a 5, for instance, in that set of numbers? Okay, how do you determine that? The very best you can do, okay, is start with the first number and compare this number with the value you are looking for. Okay, so with all of these searching algorithms, okay, the basic operation that we are using is comparison, because we need to compare two numbers, right, over and over again. We want to know, is there a 5 in this set of cards right here? Okay, I don't know. Is 7 a 5? No, it's not. Okay, so we're going to ignore that. Okay, go to the next one. Is 10 a 5? No, it's not. Is 1 a 5? No. 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 And no. No. And no. Okay, so what do we know now? We've gone through the list of cards. We reached the end of the list. We did not find a 5. That means that there is no 5 in this list. Okay? Let's reset this. I'm gonna pull this back over so we have the same list again. It doesn't really matter because the order, we have no prior knowledge about these cards. Okay? We can really only see one at a time. Okay? Now, let me ask a similar question. Is there a 3 in this deck of cards? Okay? Here's the process. Is 7 a 3? No. Is 10 a 3? No. Is 1 a 3? No. Is 9? No. 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 Ah, there it is. There's the 3. Okay? So we can return true or yes or 1, or we can even return the position that the 3 is in the list to indicate that there is a 3 in that list. Okay? So the process of starting at the front of a list, looking at each value one at a time, okay, and comparing each value at the front of the list to the number that you want to find, that is called, until you either find the number or you reach the end of the list, that is called linear search. Okay? Sometimes it's called sequential search. Those are the same algorithms, just two different names for the same algorithm. Sequential search, the word sequential seems to make sense because we look at each value one at a time in a sequence until we either find the value we're looking for or we find the end of the list, indicating that the value we're looking for is not in the list. Okay? Notice there, and we'll talk about why I've called it linear search in just a second. Notice that there are 3 possible ways to think about how expensive this algorithm is. So what do I mean when I say how expensive or sometimes how efficient an algorithm is? What does that mean? What that means is for any input of size n, okay, where n is the size of the input. In this case, the input to this problem is a list of numbers. And so n is the number of numbers in our list. In this case, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, there's 10 numbers in this list. Okay, I'm going to put them back over here. So n in this case is 10. Again, the order really doesn't matter. I'm just trying to maintain the same order just so we can keep things organized. N here is 10, okay? But in general, for any size, we say the size of that list is n, okay? So if you've got a bunch of cards, a bunch of numbers in your list, the number of numbers in your list is said to be n. The basic operation, which we said was comparison a minute ago, and it is the fundamental operation that is used in deciding your algorithm. Okay, and deciding your algorithm's output. Okay, in this case, it's comparison. The fundamental thing we do is we compare each card, each value, to a value that we're looking for. Okay, so how expensive a thing is can be defined by a function, right, that determines how many basic operations occur, okay, for a given size n input. Okay, what do I mean? All right, what do I mean? All right, so if you had a crystal ball or an oracle, and you could always just look in your crystal ball, no matter how large your list was, and determine if a value is there or not, then we would say that was constant time performance, because it takes one action, right, one basic operation, or a set number, even a set number of operations, independent of the size of the list, to always come up with the answer. So we say this is called big O notation. The O stands for order. This big O notation, it'd be constant. Okay, is this constant? Right? Okay, so let's say I'm looking for 12. Okay? How many comparisons do I need to do to find out that there is no 12 in this list? Okay? Or what did I look for last time? 5, and we didn't find it. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? There are no 12s or 5s in this list, and it took me 10 comparisons to find that. Why did it take me 10 comparisons? Because if it's not there, okay? So here's the thing. Worst case. Okay? Fell off the keyboard. Worst case. What is the worst case for looking for something in a list? Either it's the very last thing or you don't find it at all. And in either case, the number of comparisons is equal to the size of the list. So we say that it runs in big O of n time. In other words, how efficient this algorithm is a function of the size of the output, size of the input rather. Okay? So as the input size grows, the efficiency decreases. Okay? And it does so 1-to-1. So this is said to be linear search because its efficiency decreases at the same rate that the size of the input increases. Okay? So it has a linear growth is what we say. It's big O of n. Okay? Not all algorithms are going to be like that. We're going to see, especially when we look in our next lecture at sorting, we're going to see some algorithms that are worse than linear growth. Okay? So get ready for that. All right? Now you might say, but look, in the best case, how much does it cost to find out that there is a 6 in this list? Just one. It's right here. It's on the top. It's the one that I can see. Hey, woohoo, right there it is. It's a 6. I did one comparison. Okay? So yeah, you're not wrong. In the best case, the number of comparisons is equal to 1. But why don't we care about the best case very much? Okay? Because of all the numbers we could look for, the best case is limited to only one possible value to look for, right? So it is not likely. Okay, it's not likely. We care much more about the worst case. If we say, in the worst case, that the performance of a algorithm is big O of n. It equals the number of basic operations equals the size of the input, then we're saying that it can never be worse, regardless of what the input is, than linear time efficiency. Okay? And that is a very strong thing to say. You might say, look, hey, you might get lucky and it'll be really good. Okay? But we're pessimists. We are paid to be pessimists. We should think like pessimists. And we're going to ignore this very unlikely best case, and we're going to instead focus on the worst cases to tell us how efficient an algorithm is. The other thing that we might sometimes look at is the average case. Okay? So in the average case, what we do is we look at all possible numbers that we could be looking for in a given input, in a given list, and we say, on average, how much is it going to cost me how many comparisons is it going to cost me to search for a value? Okay? And turns out that in this case, for successful searches only, it's about n over 2, or 1/2 times n. Okay? But that is still, because we can drop the constant out front, that is still said to be big O of n. Okay, now I'm not going to get into the details too much at this stage about algorithmic comparison, but because there are at least 2 more classes that are going to cover this material, and then also the algorithms class itself will cover some of this material, and so you've got plenty of time to kind of wrestle with this. But what I will say is, if you've got 2 algorithms that solve the same problem, okay? If you've got 2 algorithms that solve the same problem, and you want to know which algorithm is better, okay? Then what you're going to do is you're going to look at those functions that determine how efficient an algorithm is, okay, those algorithmic efficiency functions, or the big O functions, and you're going to say, well, one of them grows more slowly than the other with the same growth in input size. And the one that grows more slowly always takes fewer operations, making it more efficient. So in this way, we learn to say something very efficient about, not efficient, but very strong, very mathematically strong about algorithms and comparing algorithms. In fact, that is the very root of the science behind computer science. Okay, I love teaching algorithms, but this is not an algorithms class, so I'm going to stop right there. But if you have questions about how I did this and how we might do this in the future, ask them, or just hang on, because we're going to have an opportunity to see a couple of different examples, both in today's lecture and moving forward. Okay? All right, so real quick, let's code up a algorithm that does linear search. I'm going to do this in a function. All right, so notice so far I've been looking at only the top element in a stack, but think about a good way to store these values. Okay? We need a way to process through these values one at a time, and we need to be able to store them in computer memory. Okay? So the way to do that is to be able to store them in you guessed it, an array. Okay? So let me see if I can spread these out so that we can kind of look at them one after another. Now, looking at them this way, it looks like I should just be able to glance and see if, for instance, there's a 5 in this array. But that's not how the computer works. The computer can't look at all of these values at once, or multiple values at once, in the way that you can. The computer still needs to be asked, is this position the value that you're looking for? Is this position the value? That's the best that the computer can do. It has to handle. It can store all of these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values. It needs to store them in 10 different positions in memory and handle those memory positions and the values in them one at a time. Just to make our lives easier, we're going to store them contiguously in memory into what we call an array. Okay? So think of this as an array. So this is position 0. This is position 1. This is position 2. This is position 3, 4, 5, 6, 7, 8, 9. Okay? So what does that look like in code? Let's do it real quick. Pound include IOStream. Okay? Using namespace standard int main. That's where we'll start anyway. Okay? And this has return 0. Okay? And we're going to create an array of integers. Okay? Of size. How many values did we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, size 10. Okay. All right, and then I'm just gonna use an initializer list like we talked about before. Okay, so we had 7, 10, 1, 9, 7, 10, 1, 9. Okay, and 10, 8, 2, 4. Okay, 10, 8, 2, 4. All right, and 3, 6. Okay, 3, 6. All right. Okay, there we go. All right, so now I want to write a function called linear search. So what I'm going to do is I'm going to have int test. All right, so I'm going to do cout. Enter a value to search for. Okay. All right. And then I'm going to read in to test. Okay. Now, while test does not equal -1. Okay. Then what? I am going to do linear search. Okay. Test and array. Okay. Passing in and the size of the array, 10. Okay. Passing in the value I want to look for, the array, and the size of the array. And I'm going to set an integer called result. In fact, we'll just do bool. Bool result. I'm going to set result equal to linear search. Okay. Then I'm going to ask again, enter a value to search for, cin test, and then we're going to repeat. So press -1 to end the while loop and terminate the program. Okay. But before I do that, I actually need to do something with the result, I guess. Cout, if result, okay, then, all right, cout, okay, found, else, okay, wrong one, cout, not found. Okay. Gotta put the quotation mark there. Okay, what am I missing? Well, I'm obviously missing the function. Okay, so here's what the function signature, the function declaration looks like. It's going to have a bool return type. Its name is linear search. Okay, it accepts a value to look for, which is an integer. It accepts an integer array, and it accepts an integer for size. Okay, the size of the array. All right, remember the function has no way of knowing how big the array is unless we somehow tell it. Okay, bool linear search. Okay, integer key. Key is just another name for a value that we're searching for. int a, okay, and int size. Now, as we learned before, okay, we have to be careful here, because if we change any value in a, okay, we are also changing values in array, because arrays are always passed by reference. We're not going to do that. We're not going to change any values in the array. We're only going to look through the values in the array. Okay. Speaking of which, how do we do that? Well, let's do a Boolean result. Let's call it res this time. So for int, and we'll set it to equal to false to begin with. For int I equals 0, I is less than size, I plus plus, so I can be used as an index to the array, which in this function is called a. Okay. If a at position I is equal to the key, okay, then that means we found it. And we found the thing we were looking for. So if we find the thing we're going to look for, we set res equal to true. Now, once we find the thing we're going to look for, we don't need to keep looking. So I'm going to put a break statement right here. And that is going to break out of the loop that it is inside of. So that means it's going to end this for loop prematurely, right? We find one instance of the key. We don't care if there are other instances. We're just going to return true, and we're going to do that without finishing up this for loop. Okay. So, like I said before, in the best case, if the for loop, if the search finds that the key is in the first element, it will only do one comparison. If it finds it's in the third element, it will only do 3 comparisons. If, however, it doesn't find it, it will do a total of n comparisons, where n is the size of the list, and that would be the worst case. It's tied for worst case with if it finds the value in the very last position. Okay, that's still in comparisons. Okay, so this is linear search. It's going to have an efficiency of big O of n, or linear time. Its efficiency is going to decrease as the size of the list increases. Okay, proportionally with the size of the list. Okay, I think that's all. So I haven't saved this yet, which is why the text coloring hasn't been working in our favor. So we're going to go ahead and do that. Let me save it someplace reasonable. This is an in-class example. This is linear search. Okay. All right, now we've got our text coloring. Of course, the only way to test this for sure is to compile it. So let's do that. All right. So let's go into the folder where it is, and we're going to compile linear search. All right, and then we'll run it. Okay, enter a value to search for. All right. So let's search for 7. Hey, found. Enter a value to search for. Let's search for 10. Found. 5. Uh-oh. Oh, do you see what we did? Didn't mean to make this error, but that's a good thing that I did. This is the great thing about live examples. They have a tendency to pop up the errors, right? All right, so do you see what we did? Where do we set result equal to false? Okay, we set it equal to false right here. Okay. No, that should work actually. What did I forget to do? Silly me, I forgot to return, right, res. Okay, now let's try it. Compile it, run it, search for 5. There we go, not found. Okay, what about 6? Found. How about 8? Found. What about 53? Not found. Okay? And so that's simple. That's the simple. Here, we'll type in -1 to quit. All right, so that's the simple linear search. Right? There's really nothing else to it than that. Okay. Now, I said linear search was going to, in the worst case, cause us to have to do n comparisons, where n is the size of the list. Now, if we don't know anything about the list, if we can't say anything about the list, then linear search is the most efficient type of search that we can do. Okay? But sometimes it's possible to do what's called pre-processing. Right? Now, it's critical to understand that this is not without cost. Right? It's not without cost. But I do want to ignore it temporarily for right now. Okay? I want to ignore this just for a second. The pre-processing, its cost anyway. I want to ignore its cost just for a second. The pre-processing act that we are going to do is we are going to go ahead and sort the list. Okay, we're going to sort the list. All right. So here is what I mean. This is easiest to do visually. Okay. All right. So let's sort this list. And we haven't talked about sorting yet, or sorting algorithms yet, and we won't until next time. But this is maybe going to help us motivate the sorting algorithm. Okay, the need for sorting algorithms. All right, and I can sort really easily because my brain can kind of like see all of this and sort of remember what values are here. But remember, a computer is limited to only dealing with one value at a time. Okay, so I'm going to make this look easy, but I can't. I'm smarter in this case with this visual acuity than a computer is, right? So what do I do when I look through here? I look through here and I find the smallest value. Oh, there it is. It's the ace. So I put it first because the smallest value is going to go first in my sorted list. Okay, I'm going to sort from least to greatest, sort of the classical way. Then I'm going to look for the next smallest thing, and I can kind of just look at it. But you can see how a linear search would be helpful, right? Find this. We've already written algorithms in the past to find the minimum thing. All right, the minimum thing I've seen so far is 7. Still 7. Still 7. Still 7. Still 7. Now the minimum thing I've seen so far is 2. Still 2. Still 2. Still 2. So the minimum thing left is 2. Well, you knew that already because you could see it, right? But that's how you teach a computer to do that, okay? The next minimum thing, the next smallest thing is 3, and then 4, okay? And then it looks like 6. Okay, and then 7, 8, 9, and then we've got a tie. There's 2 10s, and so it doesn't matter what order they go in. Okay, now all of a sudden I have a sorted list. Okay, why is having a sorted list important when you are doing searching? Think about that for a second. Why do we alphabetize the phone book? Oh, I'm aging myself. But you all know what a phone book is, even if you maybe haven't seen one in a long time or maybe have never seen one. Why do we alphabetize our list of contacts on our phone? Okay? Why is the dictionary alphabetized? Why is ordering things important to us? Ordering things makes things easier to search. How so? Okay? Well, consider this, right? Consider that I can still do linear search on this list. I want to know if there's a 5 in this list, okay? Is 1 a 5? No. No, 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 no. Okay, so there are no 5s. I can still do linear search on this list. But if I know ahead of time that the list is sorted, then is that the most efficient way to do a search, right? Notice that the first time I found a value, right, bigger than 5, it means that 5 cannot possibly be down here because all the values past this one are also bigger than this one, which means that they are bigger than 5, right? So when you go looking in the dictionary, if you pick up an actual physical dictionary and you go looking for the definition of a word, right? Let's say I give you the word catastrophic, okay? You are going to, if you don't know anything else about all the words in this dictionary might have C's, might start with C's, okay? Just like we don't know anything about these numbers, they could all be aces, okay? Because this is the only one we can see as the computer, right? So the best thing to do is to open the book up to the middle, okay? So here, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We're gonna pick a middle element. We're gonna, if they split evenly, we're gonna pick the left-hand side. Okay. I want to know if there is a. Let's do 5 again. I want to know if 5 is in this list. So jump to the middle of the list and compare the value in the middle of the list to the thing you're looking for. It's a 6. So if 5 is in this list, okay, then it means what? It means it can't be out here. So we can ignore that whole half of the list. It must be in this part of the list, okay, the first half of the list. So is there a 5? Well, let's look at the middle part of this half of the list. No, this is a 2. So if there is, here, let me try and go down here. If there is a 5 in this list, it must be over here, right, to the right-hand side. So we can ignore the left-hand side. Let's look in the middle, all right? Is there a 5 right here? No. This is the only thing left. Is that a 5? No. So what does that mean? It means that there is no 5. Now, how many comparisons did we do? We did 1, 2, 3, 4. To run an unsuccessful search using linear search, it took 10 comparisons. Okay? To run an unsuccessful search using binary search, which is the process we just did, that look at the middle element, go either to the left or the right, ignoring the other half of the list, that's called binary search. Okay? It took only 4 comparisons to find that the number wasn't in the list. Okay? Why? Because we got to ignore half of the remaining list every time. So that makes our algorithm more efficient. What does this cost? It actually costs big O of log n. It's actually log base 2 of n. But this is so common that you'll just generally see this left off in computer science. So it's big O of log base 2n. Okay? If you plot a graph of log n and n side by side, okay? Here, let's see if somebody's already done this for us. Okay, graph of log n versus n. Okay. No, that doesn't have what we want. It's sort of like what we want, but not quite. I don't know if anyone's done it for us. There are various things. Oh, here we go. Okay, great. All right, so this is big O of 1, right? This is the increase. This is n as the size of the input increases. This will be the number of required operations to finish our algorithm. If it always takes a constant number of operations, then we get this flat line called constant time that's always flat no matter how big n gets. Notice big O of n splits the difference at a 45-degree angle. So it grows at the rate that n increases. It has a linear, it's a line, it has a linear increase with the number of basic operations that get performed, right? So that's why that's called linear search. Okay? Log n, after a critical point here, grows considerably slower than n. Okay? And so what this means is that if I have an algorithm like binary search that has log n performance, then as n increases, the performance gap between log n and n also increases. So like if we had a million cards to look through to find a item, a million values to look through to find a particular value, then big O of a million is a lot more than big O of log 2 a million. Okay? So the more slowly that the function that determines the number of basic operations for the algorithm grows, the more efficient that algorithm is. And so more efficient algorithms are in some sense better, I'm using air quotes, but better algorithms, okay? We like those more efficient algorithms over the less efficient algorithms, okay? Now, like I said, this pre-processing actually comes with a cost. It takes time to convert a unsorted list into a sorted list. That's not free. And we'll talk about algorithms for doing that and how much they cost in the next lecture. But if you're comparing the best possible performance with an unsorted list, which is linear search, and the best possible performance with a sorted list on which we can use binary search, then you're much better off in the long run, especially if you're doing a bunch of searching, to have a sorted list to start with. Okay? All right, so this is somewhat different. The code is not the hard part here. The code is fairly easy. Now, there's a complication when it comes to binary search, which is why I didn't show you a code for binary search, because in binary search you always have to be able to find the middle, which we can do, but I didn't want to complicate things when you're just now learning to use arrays. We might come back and loop back around and show that again later on. But generally the code is very simple. This is not a coding problem. Most of computer science is not coding problems. Most of computer science is in figuring out what's the best way to code, what's the most efficient way to code. And so, yeah, this is kind of our first foray into the actual science of computer science. So I expect that you may have to go back and watch this lecture again. You may have to read. You may have to go look at other lectures. This is not easy stuff conceptually to kind of wrestle with, but it's very important stuff, especially in the long run, to wrestle with. And we're gonna keep wrestling with this kind of algorithmic efficiency as we move forward into talking about. Sorting algorithms. Okay, I'm gonna have to try and remember to move this cursor out of the way so that so I don't have a cursor sitting on my face or something bothering you. Anyway, learn as we go, right? Okay, so that's the end of today's lecture. Lecture on searching. Be looking later in the week for the next lecture on sorting. I hope you're healthy and well. I hope you're safe, and I hope you're doing fine. And if you have questions, let me know. I'll see you next time.